Welcome to the deep dive. Today we're going to be looking at some really cool physics research
Yeah,
about how magnetic fields could change the future of electronics.
definitely cutting edge stuff.
It all starts with this article from SciTech Daily. Physicists unlock the potential of in-plane magnetic fields for advanced magnetotransport.
Mm-hmm. I
And
think the thing that's so interesting about this is it's not your typical, north-south magnets.
Right.
This is like a whole new way of thinking about magnetic fields and how they can be used.
yeah, okay, so we all know how magnets work, like compasses point
Yeah.
north.
Right.
But this research is talking about magnetic fields acting within the plane of a material.
Yeah, like alongside it.
So, what's the big deal with that?
Well, I mean, you know about the Hall effect, right?
Of course.
Where a magnetic field perpendicular to a current-carrying material creates a voltage.
Yeah, it's like physics 101.
Exactly. Like it's a fundamental principle,
Mhm.
but this research uses the magnetic field in a completely different way.
Yeah.
Like instead of perpendicular to the material, it's applied parallel to it.
So it's like we're taking that same principle and flipping it on its side.
Exactly.
Instead of the magnetic field acting like a barrier, it's now running alongside the current.
Yeah, and that opens up all these possibilities for manipulating the electrons
Right.
and creating materials that have completely new properties.
So to explore this idea, they focused on this material called
EuCd₂Sb₂.
EuCd₂Sb₂.
Yeah, it's a mouthful.
Got it.
But it's a really interesting material because it's super sensitive to these in-plane magnetic fields.
Okay, so why is that?
Well, it has to do with its electronic structure.
Uh-huh.
Specifically, these things called singular points.
Singular points.
Yeah, and these points are basically like super sensitive zones where the energy bands of the material intersect.
Okay, I'm following.
And so they act like amplifiers for the in-plane magnetic field,
Interesting.
making the Hall effect much stronger than normal.
So these singular points are like finely tuned antennas, picking up on even the slightest whisper of a magnetic field.
Exactly.
And boosting its impact, but what kind of impact?
Well, what they found was that when they applied the in-plane magnetic field to the EuCd₂,
Okay.
it created this large and unusual Hall effect.
Oh, wow.
But here's the really wild part.
Oh.
The effect actually flipped directions,
Flip directions.
depending on which way the magnetic field was pointing.
Wait, hold on.
Yeah.
So the direction of the magnetic field dictates the direction of the Hall effect.
Exactly.
It's not just about the strength of the field, but the orientation.
That's right. It's like imagine a clock face and the magnetic field's pointing at 12 o'clock.
Okay.
The Hall effect goes one way.
Uh-huh.
Rotate the field to 4 o'clock, it flips.
Wow.
Rotate it to 8 o'clock, it flips back.
Okay.
So it has this threefold symmetry,
Threefold symmetry.
which reflects how the atoms are arranged within the EuCd₂ crystal.
Okay, that's pretty cool.
Yeah, it's like the material has this built-in compass that responds to the magnetic field in this very specific way.
But why is that threefold symmetry such a big deal?
It's not just a quirky pattern. It's like a fundamental signature of the material's inner structure.
Interesting.
And that connection between symmetry and the material's properties is huge.
Yeah.
It means we could potentially use this knowledge to engineer new material
Oh, wow.
with specific magnetic responses.
So it's like we're cracking the code of how these materials behave
Yeah, at the atomic level.
at the atomic level.
Exactly. And that's really just the tip of the iceberg.
Okay.
This discovery could have really far-reaching consequences,
Like what?
especially when you consider something called orbital magnetization.
Orbital magnetization.
Yeah, have you heard of that?
I have not.
Okay, so basically it's all about the electrons whizzing around the atom's nucleus.
Okay.
They're like these tiny little magnetic tornadoes,
Uh-huh.
creating their own magnetic fields as they orbit.
Okay.
But normally these fields cancel each other out at a larger scale.
So each atom is like a tiny solar system
Perfect analogy.
with its own set of magnetic forces.
Yeah, but what's interesting is that in UCD,
Okay.
the in-plane magnetic field actually enhances this orbital magnetization, making it way more significant.
Yeah.
And it's this enhanced orbital magnetization that contributes to the large and unusual Hall effect we are talking about.
So the in-plane magnetic field unlocks this hidden magnetic potential
You got it.
within the material.
And this opens up a whole new way of thinking about how we can control and use magnetic properties in materials.
Okay, that's really interesting. So where does this lead us?
Well, I think one of the most immediate possibilities is in magnetic sensors.
Magnetic sensors.
Yeah, imagine sensors that could detect even the tiniest fluctuations in magnetic fields
Okay.
with incredible precision.
That would be a game changer
Oh, absolutely.
for so many fields.
Think medical imaging, navigation, even geological exploration.
Wow.
This research could lead to sensors that are way more sensitive and reliable than anything we have now.
So we're talking breakthroughs in healthcare transportation resource management.
Yeah, the list goes on.
The list goes on.
And beyond those specific applications, there's this whole world of spintronics.
Spintronics?
Yeah, this field uses the spin of electrons to make new electronic devices.
That sounds super futuristic.
It is, and this discovery could be a major step forward. Like, imagine transistors and other electronic components that are smaller, faster, and more energy efficient than anything we can build today.
That's mind-blowing.
Right.
But this is all still early-stage research, right?
Yeah.
We're not going to be seeing, like, spintronic smartphones anytime soon.
Not quite, but this research lays the groundwork for some revolutionary technologies.
Right.
It's a good reminder that the most profound changes often start with the smallest steps.
So it's like we're seeing the birth of a new era in material science and electronics.
Yeah.
Where manipulating magnetic fields could unlock a whole new world of possibilities.
Precisely. And it all starts with understanding the fundamental principles of how materials interact with these forces.
This has been a really fascinating deep dive into the world of in-plane magnetic fields and the Hall effect.
Yeah, definitely some interesting stuff.
We've uncovered some truly groundbreaking research that has the potential to revolutionize our understanding of magnetism and its applications. But before we get too carried away with the possibilities, let's take a closer look at some of the specific findings from this study.
Yeah, let's dive into the details. One of the things that I think is so cool about this is, they weren't even looking for this unusual Hall effect. It was just pure scientific curiosity. Like they were exploring the fundamental physics of these in-plane magnetic fields and boom!
Wow.
They stumble upon something groundbreaking.
It's like those explorers, setting out to find a new trade route.
Yeah.
And they end up discovering an entirely new continent.
Exactly. And it really highlights how important it is to support this fundamental research, even if we don't know what the practical applications are right away.
Right.
It's about pushing the boundaries of what we know. Who knows what incredible discoveries are out there just waiting for us?
It really does make you wonder, what other secrets are hidden in the universe.
Yeah.
Just waiting for us to stumble upon them.
Yeah.
Okay, let's bring it back down to Earth for a second.
Okay.
How could this research actually impact people's everyday lives?
Well, think about it. Imagine a world with these super sensitive magnetic sensors.
Okay.
That could pick up on the faintest signals.
Uh-huh.
We're talking about detecting everything from tiny changes in brain activity to underground resources.
Oh, wow.
It could revolutionize healthcare navigation resource management.
That sounds like something straight out of science fiction.
I know, right?
Like these tiny little sensors unlocking a whole new level of understanding.
It really is mind-blowing.
About the world around us.
And it goes beyond just those specific applications. This discovery could change how we design and build electronics entirely.
Oh, wow.
Imagine computers and smartphones that are hundreds of times faster and more energy efficient than what we have now.
That's a really tempting thought.
I know.
But like you said earlier, it'll probably be a while before we see those devices in stores.
Oh, yeah. Of course, scientific progress takes time. But this research is a huge step forward.
For sure.
And it's exciting to think about where it could lead us.
Now let's go back to that threefold symmetry thing for a second.
Yeah.
Why is that symmetry such a big deal?
Well, it's not just a coincidence.
Right.
It's a direct reflection of the material's structure, like EuCd₂Sb₂. Think of it like a snowflake.
Okay.
It has six-fold symmetry.
I see.
Meaning it looks the same if you rotate it by 60 degrees.
Okay. Yeah, I get it.
So the atoms in EuCd₂Sb₂ are arranged in a specific way that creates this threefold symmetry.
Right.
And that dictates how the material reacts to the in-plane magnetic field, which leads to the threefold symmetry we see in the Hall effect.
So it's like the material is telling us its secrets through this pattern.
Exactly.
But how do they actually measure that symmetry?
They use this cool technique called angle-dependent magnetotransport measurements.
That sounds complicated.
It's basically applying the magnetic field at different angles.
I see.
And then carefully measuring the Hall voltage.
Yeah, so they were rotating the magnetic field around the material.
Exactly.
And seeing how the Hall effect changed.
Yeah, and by plotting the Hall voltage against the magnetic field angle, they saw this clear threefold symmetry.
Oh, wow.
It was a beautiful confirmation of how the material's structure and its magnetic behavior are connected.
Okay, so let's talk about practical applications.
Okay.
What kind of devices could we build with this?
Well, the possibilities are pretty much endless.
Wow.
But let's start with magnetic sensors.
Uh-huh.
Imagine a sensor that could tell you the direction of a magnetic field super accurately. That could revolutionize navigation systems.
No more getting lost.
Exactly.
I like it.
These sensors could also be used in medical imaging to create really detailed maps of brain activity.
Oh, wow.
Or in geological surveys to find mineral deposits or water sources.
The applications really are endless.
Yeah. And what about the impact on computing and electronics?
That's what I'm really interested in.
Me too.
Yeah?
This discovery could lead to a whole new generation of electronics.
Oh, really?
Based on using these in-plane magnetic fields to control the Hall effect.
So instead of traditional transistors, we could use this new phenomena to control the flow of electrons.
Imagine transistors that are way smaller, faster, and more energy efficient.
Oh, wow.
That could lead to a computing revolution.
A revolution.
We could build devices that are way more powerful than anything we have now.
It's hard to even imagine that kind of change.
I know, it's huge.
It's like we're talking about something that could reshape the entire tech landscape.
Yeah, it's pretty mind-blowing.
But it's important to remember that even the most massive advancements often have really simple beginnings.
Absolutely.
Like, think about the discovery of the electron.
Right.
This tiny particle that changed how we understand the universe.
Exactly. And this research on in-plane magnetic fields and the Hall effect could be one of those pivotal moments.
Yeah.
It's a reminder that the world is full of mysteries. And that the pursuit of knowledge often leads to these incredible discoveries.
This deep dive into cutting-edge physics has been amazing.
I agree.
We've uncovered research that could revolutionize so many things.
Yeah.
And it's been a good reminder about the power of scientific curiosity.
Definitely.
And why it's so important to support fundamental research.
Couldn't have said it better myself.
But before we get too lost in all the possibilities, let's step back and think about the scientific process itself.
Right.
Because this research didn't just come out of nowhere.
Yeah, it was a journey.
A journey of exploration, experimentation.
And discovery. Yeah, it really is a winding path, you know, full of twists and turns and unexpected discoveries.
Right.
It's important to remember that this research, you know, didn't happen overnight. There were probably a lot of dead ends and challenges along the way.
It's like watching one of those nature documentaries.
Yeah.
You see a pride of lions stalking their prey.
Right.
It's not always a clean and efficient hunt.
Definitely not.
You know, there are setbacks, adjustments, moments of improvisation.
Absolutely. And in this case, the researchers started with a pretty simple question. How do these in-plane magnetic fields affect this material, EuCd₂Sb₂?
Right.
And to figure that out, they had to design these really careful experiments, controlling the magnetic field and measuring how the material's conductivity changed.
There's a lot of trial and error. Careful observation, constant refinement.
Exactly. It wasn't easy.
And I bet they ran into some unexpected results along the way.
Oh, I'm sure they did things that didn't fit their initial ideas. But instead of just ignoring those anomalies, they dug deeper, looking for explanations.
And that's what ultimately led them to this unusual Hall effect.
Exactly.
And the threefold symmetry.
It's a perfect example of scientific curiosity in action.
Right, like embracing the unexpected.
Yeah, this is what we call scientific serendipity.
Serendipity.
When an unexpected observation leads to a major discovery.
I like that.
And it shows how important it is to stay open to new possibilities, you know, to challenge our assumptions.
Yeah.
And let curiosity guide us.
So speaking of mysteries, let's talk about this large, unusual Hall effect they observed.
Okay.
What makes it so unusual?
Well, typically you see the Hall effect when a magnetic field is applied perpendicular to a material.
Right, like holding a magnet above a wire.
Exactly. But in this study, they applied the field parallel to the material.
Okay.
By putting the magnet next to the wire.
Interesting.
And what they saw was really surprising.
What was it?
Not only did the Hall effect still happen, but it was way bigger than usual.
So it's like they flipped the script on the classic Hall effect.
Exactly.
And got this supercharged version.
And that's why everyone's so excited about this research.
Right, it's like a whole new set of possibilities.
Yeah. For how these in-plane fields can interact with materials.
Now, the article also mentioned orbital magnetization.
Oh, yeah, that's a key part of this.
Can you explain that a little?
Sure. So basically, it's all about the electrons orbiting the atom's nucleus.
Okay.
Each electron creates its own tiny magnetic field as it orbits.
So each atom has its own little magnetic field?
Yeah, like a mini current loop.
Got it.
Now, in most materials, these fields cancel each other out. But in some materials, like EuCd₂,
right,
the in-plane field can actually boost this orbital magnetization.
Interesting.
So it becomes a major factor.
So the in-plane field amplifies these hidden magnetic properties.
That's a great way to put it.
And that's what contributes to the large Hall effect.
Exactly. And this connection between the field, the singular points, and the orbital magnetization is what makes this so groundbreaking.
It's like we're learning how to control these fundamental forces.
Yeah. And who knows what we'll discover as we keep exploring.
Maybe a whole new era of material science.
It's definitely possible.
Now, before we wrap up, I want to touch on that comment from a reader who is skeptical.
Yeah, it's understandable that people might be hesitant.
Right, when research challenges the way we think.
But healthy skepticism is important in science.
Of course.
It makes us question things and demand evidence.
Right.
And this research has been peer-reviewed, meaning other experts have checked it out.
Good point.
So while there's always more to learn,
Yeah,
these findings are a big step forward in our understanding.
it's a good reminder that science is a process.
Right.
It's about constantly exploring and questioning and refining our knowledge.
And it's through that process that we make progress.
Well said. So, as we move forward,
Yeah,
it's important to encourage open dialogue and critical thinking,
absolutely.
and to be open to new ideas.
Even if they challenge what we think we know,
That's how science moves forward.
that's how we unlock new possibilities.
This has been an amazing deep dive.
I agree.
We've explored groundbreaking research
Yeah,
that could change the world as we know it.
it's been a really thought-provoking discussion.
And we've learned about the power of scientific curiosity.
And the importance of supporting fundamental research.
So on that note, we'll wrap up this episode of The Deep Dive.
Thanks for joining us.
We hope you enjoyed this adventure into the world of cutting-edge physics.
Keep exploring, everyone.
And until next time, keep questioning.
And never stop learning.